I think many people know he's from. He did his PhD from UC San Diego, then at Princeton, and now he's at Caltech.
Yeah. Okay, thanks for the invitation. So today I'll be talking about universality in spin-refined high-energy data in higher dimensional CFT. So the idea is we all know that in CFT, oftentimes the high-energy data, like high-energy density of states. Yeah, I think it's turned on. Yeah, I think it's turned on.
I think this Gurita Viber knows, but he has not known.
Yeah, there's a red. I guess if it's red, it's recorded.
Okay, good. So as I was saying, the high energy data in conformal field theory are often universal, like high energy density of states, and so on. And so today our goal would be to look at this high energy data, high energy density of states, and ask a refined question about how this density of states gets distributed among different spin sectors. And in 2D, like these kind of questions can be answered using modular invariance because that's an extra constraint on the partition function. But in higher dimensionals, for higher dimensional CFT, when we are considering putting the CFT on S1 times SD minus 1, there is no as such modular invariance because there are no two cycles which we can exchange. But then today the goal of the talk would be to convince you that in higher dimensional CFT, we can also write down some effective field theory which characterizes this high energy density of states. And once we write that down, we can also ask about the spin refined data, high energy data. And once we write down the EFT, those comes with some Wilson coefficients, and this spin refined data will be determined by those Wilson coefficients. So the motivation is to like build a framework which replaces the modular invariance and which plays the analogous role of modular invariance for higher dimensional CFT and gives us some handle over the high energy data. And of course these are universal, so that's why they are useful. And another motivation of studying these quantities is to think about ADS CFT, and this high energy data often encodes the black hole physics. For example, you can compute the density of states, you can compute entropy, and then you can match up with the entropy of a black hole in appropriate ADS spacetime. For example, in 2D CFT, the Cardy formula relates to the entropy of the BTZ black hole. So to set up the stage, I will first start with our old two-dimensional CFT and explain you how modular invariance gives you some set of results. And then we will look for similar kind of results in higher dimensional CFT, and we will see how we can do that in higher dimension. So to let us begin with, and all this work is based on this paper, which we put out last month and with all the Caltech people, Nathan, Jeha, David, and Ishin. Okay, so let us begin with two-dimensional CFT. So in 2D CFT, we consider a unitary one, and in 2 dimension we have modular invariance. So the partition function satisfies some property, and this immediately tells you that the density of states at high energy, where the delta goes to infinity limit, is given by this universal formula 1/4 exponential twice pi c delta over 3. And the main point of this formula is that this formula is universal, and by universal I mean it is controlled by a single parameter central charge, controlled by a single parameter which is the central charge. And of course, as you might remember from January, that I mentioned that a proper way to interpret this kind of formula is to smear this density of states over some small window, and then this smeared or average density of states have this smooth approximation given by the Cardy formula. So, but in today's talk, I will not be dealing with microcanonical ensemble, Rather, I will be phrasing this universality in terms of canonical ensemble. So another way of phrasing the same kind of universality is to write down the partition function z of beta, which is same as trace e power minus beta h, and this formula is equivalent to this statement that in the limit beta going to 0, you have this universal expression 4 pi square over beta c over 12. And again you see that there is a single parameter, the same central charge appears here. So there is a universality. And you can make this formula a little bit more specific. You can insert a spin I omega j, and then it gets modified slightly, and you have exponential 4 pi square over beta 1 plus omega square, and again c over 12. The upshot is that the high temperature behavior of this kind of partition function is controlled by a single parameter. Once you know this parameter central charge, you can determine this. And the usual way of deriving this formula is to take this expression and do an inverse Laplace. But as I was saying, we will only focus on canonical ensemble quantities in this talk. So if you recall that to derive this formula, we basically use S modular transformation, which is the statement that z of beta is same as z of 4 pi square over beta. You take beta going to 0 limit, so in this channel this is basically a low temperature limit because it's 4 pi square over beta, and then everything gets projected to the ground state, and the ground state has an energy which is minus c over 12. So this immediately tells you that beta going to 0 limit is controlled by this quantity. But now we know that in two-dimensional CFT is the partition function is not only symmetric under this S modular transformation, rather there is a huge class of transformations which are the modular group is PSL2G. So PSL2G, and the partition function is invariant under this any group element gamma belonging to this PSL2G. And you might ask that whether this other group transformation, which is not S transformation, can buy us something new. And indeed it turns out that if we want to do something spin refined, then it is useful to use this kind of modular transformations. In particular, let us ask what is the behavior of trace e power minus beta h minus 1 to the power j. So now because I have inserted a minus 1 to the power j, that means it wears the even spin with the plus sign and the odd spin with the minus sign. So roughly speaking, this under inverse Laplace, this will have some information about.
So you're trying to find a bound that is stronger than that or something like that with omega some choice?
Yes. So yes, exactly. So the information that it encodes is slightly different than the information this encodes. Yeah. So here, if you do an inverse Laplace, you will basically get an information about density of states for an order 1 spin. But here, the information you will access to is basically rho even minus rho odd. So it's a more refined data where basically you are summing over all the.
No, I'm saying the right hand side. That is, if you set omega equal to some particular value, you.
No, so that will be the main point. That if you set omega equals some, yeah, you will see that.
So this is somewhat stronger.
In fact, yeah, you will see that if you just try to set beta omega, if you write it in terms of this thing, then this is basically e power twice pi I half j. So that means beta omega is half. But now imagine here I am taking beta to 0. So beta omega goes to 0. But if I want to fix omega will blow up, but there is a pole here. So which basically means that this form, so I cannot just substitute.
Yeah, so this bound is too weak in some sense.
Yes. So this formula will break down. And another way of saying thing is that if you take this quantity and do a S modular transformation, so here it was clear, and after the S modular transformation, the ground state dominates. But here, if you do the S transformation because of the
You have to do some other modular transformation
yes.
to get to the ground state.
Yes, exactly. So that's the exactly. That's the main point. Yes. So it will have some information about this quantity. So basically, it will tell you that there is a full density of states, and in the leading order row even and row order same, and then there are some bumps or fluctuations, and these fluctuations are captured by this quantity. So this will be some subleading information. So how do you determine this? To determine this, we write down the partition function in the usual way, where I have L0 over C over 24 twice pi I tau bar L0 bar 24, and if I match up this thing, then tau will be I beta over twice pi plus half, and tau bar would be the complex conjugate. And this half basically keeps track of the fact that is e power twice pi I half times j. Now the idea is to do a transformation, do a different kind of modular transformation, which is not S, rather the following one, which is -1, 0, -1, 2. So this basically acts on tau and maps it to minus tau twice tau minus 1. And if you do this, then you will see that in the dual channel, the tau prime would be I 4 pi square over beta 1/4 plus half. And now you can take beta going to 0 limit, this goes to infinity, so everything gets projected onto the ground state. And then if I plug everything in, you will see that the behavior will be exponential 1/4 4 pi square over beta C over 12. Now you see that like the difference between this thing that sits inside the exponential and the thing that sits inside this exponential is this factor 1/4. So if someone tells you that the high temperature behavior of the partition function, that is if someone tells you the central charge, you can immediately predict how this quantity will behave. So in some sense this quantity is not an independent quantity, rather it's completely determined if you know this formula. So the grand canonical ensemble, so another way of saying things, this subleading information about rho even minus rho odd is controlled by the leading information which comes from the Cardi formula. And this magic happens because of the modular transformation. And you can be a bit more sophisticated. You can also insert a e power I beta omega j on top of this, and then the effect will be you will be inserting a 1 plus omega square here. And then you will be comparing this formula with this formula. Again, the statement is this factor 1/4 appears, and there is a universality. Now you can play this game a little bit in a more general way. Instead of minus 1 to the power j, you can insert e power twice pi I p over qj e power I beta omega j, and ask what happens in the beta going to 0 limit. And now you cannot use this transformation anymore, rather you have to use some other transformation which looks like q minus p. This is minus p inverse in modular arithmetic of q, and then there is some parameter s which makes it a PSL2Z matrix. And again you do this modular transformation on tau, you do some bunch of math, some simple algebra, and then if you take the limit, then you will see the formula is following 1 over q square 4 pi square over beta 1 plus omega square c over 12. So the point is, as soon as you knew this behavior, you can predict the grand canonical ensemble with any rational amount of rotation. They are all fixed by the modular transformation. So this is the story in 2D. Now we want to ask whether something's. Sorry, say that again. Yes, this transformation is very special. Yes. Yes. So if you do some other transformation, what will happen? So, well, of course, after this you can do any kind of T transformation, and the result will not change because the T transformation only shifts the spin, and the spins are integers, so nothing will happen. But if you use some other S transformation on top of that, what will happen, you cannot prove that the ground state dominates. So it's the same logic. Here for example, you cannot use just the S transformation, because after you do the S transformation, you cannot show the ground state dominates. In fact, it doesn't. So only after this transformation, modulo T, the ground state is dominates, and you get this universal answer. Yes, because the ground state energy is given by the C/12, and the effective, so the point is the effective temperature here has extra factor of 1/4. So when you do the modular transformation here, there is no 1/4 factor in the S transformation. Here there is a 1/4, and in general you will have 1/q². So now we want to ask whether something similar happens in higher dimension. And by that I mean I want to make this question very, very precise. So the question is following. So first we want to show that in higher dimension the trace e power minus beta h has some high temperature expansion. And by that I mean that we will be aiming towards some expansion of this form, and I will make this thing precise. D plus 1, D plus 3, and so on. So first we want to show that something like this is reasonable, that this happens, and I will specify what these coefficients A0, A1 and what the systematic expansion is. So that will be the analog of the original Cardy formula I wrote down. And then I will be asking what is whether I can determine this quantity. So to begin with, this quantity will also have some kind of expansion, and with some different set of coefficients, 3 and so on. But now the question is whether the primed ones, the primed Wilson coefficients, are related to the unprimed ones. So for 2D you can see that this is basically 1/beta and the series truncates, and A0 was exactly 4 pi square over beta, 4 pi square over C/12, and A0 prime has just an extra factor of 1/q². So indeed in 2D A0 and A0 prime are related. So the question is whether in higher dimension we can write down these two expansions and can relate these Wilson coefficients, and we also ask whether there is any new features, whether there are new features because of this thing. Because of course in higher dimension we do not have the modular invariance. So even if we can predict something, there might be some new data that we have to give to completely determine this quantity. So I will also classify for which kind of cases you have to give new informations. So is the question clear? Good. What is so there is no modular transformation. So what I will be doing, I will be writing down some effective field theory, and I will invent a completely new trick to prove the 2D result, and this new trick or new idea will generalize to higher dimension.
How are the prime related
So for example, you mean what are the explicit relations? So that will only, so there are some explicit relation which I will write down. So that will only come after after I write down the thermal effective field theory. For example, at this point, the only thing I told you is that in 2D, the series truncates, only A0 and A0 prime are there, and there the relation is by this 1/q² factor. Yeah. In fact, I can give you so it will be 1/q to the power d, where d is the dimension. Yeah. I haven't explained you yet, so I will now. The next task is to explain how this series appears. Yes. Good. Let me erase this. So I want to write down the 2D result here. So what I have shown you is log trace e power minus beta h e power twice pi I p over qj in 2D goes like half log trace e power twice beta h, or sorry, this is q. So if you just plug in this exponential, you will see that something like some relation like this holds. So I want to keep this in mind, because at the end of the day I will be showing something like this also holds in higher dimension. Good. So now let us first forget about this quantity and just look at trace e power minus beta h. In fact, we can look at trace e power minus beta h e power I beta omega j directly. So what is this? This is basically a partition function on some manifold S1 times SD minus 1, and where basically this I beta omega tells you that as you go along the thermal cycle, you basically twist your S1 by this amount beta omega. So that's the path integral representation. So basically another way of saying is that this theta tau is identified with theta minus beta omega and tau plus beta. Now the basic idea is the following, that I am interested in this path integral in the beta going to 0 limit, and in the beta going to 0 limit this thermal cycle shrinks. So effectively I am looking at a theory which only lives on the base manifold, which is SD minus 1. So the idea is that I should be able to write down some effective field theory which is one dimension lower, and this effective field theory has this structure. Now how do I formalize this idea of writing down this effective field theory? So for that, instead of looking at SD minus 1, I will be starting with this thing, S1 times MD minus 1, some manifold. And again the idea is that this manifold has some like rotational isometry, and as you go along the thermal cycle by beta, your MD minus 1 gets slightly twisted by this beta omega term. And this MD minus 1, of course this whole thing has a metric. Because of this identification, it immediately tells me that the metric on this whole manifold can be written down in the Kaluza-Klein form, which is following. Some gauge field AI which takes care of the fact there is a rotation and there is a dilaton, and then there is a Gij, which is basically the metric on the MD minus 1. So the main point is this AI, this dilaton field phi, and this Gij, little Gij, all are functions of MD minus 1.
Typically, even if you did not have an omega, this would be the answer, right?
Then A will be 0.
Even if you did not have an omega?
Yes, if you do not have omega, then A will be 0. Yes.
So A will take care of the twisting?
Yes, that's the holonomy that takes care of the twisting. Yes. Right. Yes. So there is a connection with the. So they did a long wavelength expansion, and they arrived at these expressions considering hydrodynamics, and effectively they are the same expansion. I am just phrasing it in the language that has been recently been around. Yeah. Yes. So if you take that hydrodynamic action, so they have dissipative terms and non-dissipative terms, and if you just evaluate that in the equilibrium configuration, the dissipative terms will go away and the non-dissipative terms will give you what I am going to write down. Yeah. Okay. So now the next idea is that under this, when I am taking beta going to 0 limit, I am doing a KK reduction, and if the CFT is strongly interacting, generically I would not expect there will be any 0 mode under this KK reduction. So basically I can also think of it as a gap theory on MD minus 1. And then the idea is that in the beta going to 0 limit, I should be able to write it down as some effective action which
what
are
do you mean by zero mode here? So
under the KK. So just think about scalar field theory. So under the KK reduction, there could be zero mode. In fact, for example, in the free scalar field, there is a zero mode. And if there is a zero mode, then you have to take care of the contribution of the zero mode in the effective action.
so if in the KK reduction, that corresponds to the n equals zero mode.
Yeah, exactly. So but you would expect that in a strongly interacting theory, there is always a thermal gap, and which goes like 1 over beta. So in the beta going to 0,
For QCD, it will be lambda QCD.
yeah, things like that. Yes, and it's not like that. If there is a zero mode, everything breaks loose. You just have to keep track. Yes, exactly. You have to keep track of this. And as you can see, the log term are very subleading in this expansion, but you have to keep track of that then. Yeah. So for simplicity, just assume that there is no zero mode. So now I have these fields. Now I haven't used the fact that there is a while invariance, classical while invariance. So I can also use the while invariance to absorb the dilaton in this Gij. So I can also write it down as e power s thermal G hat Ij phi equals 0 and Ai, where G hat is e power minus phi G. And there can be anomaly term, which we have to choose some scheme and figure out this anomaly term. But when I say that, and the point is that when you compute this quantity, there is a ground state energy. So you have to choose a scheme, and in that scheme you figure out the ground state energy. And in the same scheme you have to figure out this anomaly coefficient also. So there is some scheme dependence, but the point is in this equation the scheme dependence goes away from both sides. So the main focus will be on this S thermal piece. Now basically what we have to write down? We have to write down this an effective action which is a function of G hat and function of Ai, which satisfies the diffeomorphism invariance, scale invariance.
Roughly speaking, you will write that if you are working with this 2D CFT energy, it will be delta plus some C type of.
Yes,
that will be the zero energy, right? Is that what you call the scheme independent? There will be delta plus.
Oh, the scheme dependence, for example, in the trace anomaly, there could be extra pieces which generally we throw away. So there is a Ricci scalar term,
right.
But there is a B type anomaly.
Yeah.
Generally we set them to 0.
So if no, I'm trying to think about it from the left hand side. So right hand side, I think I understand.
Oh, left hand side, it basically you can think of is dilatation plus epsilon naught. Yes.
That's right.
Yes. Yeah. Right. Exactly. Yeah.
And the claim is that scheme dependence at epsilon naught and the anomaly scheme dependence are the same.
Yeah.
They're matched in some sense.
Yeah. So
this piece that you get here is somehow invariant.
Yeah, so this piece takes care of the density of states and like the information about the high energy. Yes, right.
And that's basically just like a standard two derivative expansion.
Yeah. Yes, exactly. So I'm going to write down the expansion now. Okay, I am using the board space is a bad way, but anyway. So the expansion is the following. So it will be an integral of the base manifold md minus 1, then you will have an determinant square root g, and you can scale out the factors of beta. So just by dimension analysis there will be beta to the power d minus 1, and then there will be terms like f0 plus, so which is a constant piece, then the second term will be c1 times the Ricci scalar times beta square, plus then we'll have another coefficient C2 and then f square. This f comes from this AI, beta square, and so on. And the main point is that this coefficient f0, C1, C2, these are CFT dependent. So once you know the CFT, you know these Wilson coefficients. And then you can put your CFT on any background, md minus 1. You just have to evaluate this Ricci scalar and f square for that particular manifold, and you have to just evaluate it. So for any manifold, they will always come with this f c1, c2, and the rest of the things are completely determined. So in some way, we are basically separating out the UV physics and the physics at the, like in the beta going to 0 limit. So this f0, c1, c2 is some data that you have to give me for defining the CFT. So at this point I can set md minus 1 to sd minus 1 and I can evaluate this quantity. So S thermal sd minus 1 would be the following: the volume of sd minus 1, then there will be product of 1 plus omega I square. So here I didn't mention that in higher dimension you can have multiple Cartan direction because the rotation group has a higher rank. So instead of omega j you can do this omega I j I. So you can turn on omega in various directions and that will be captured by this 1 plus omega I square. So you have this factor, and then there is a factor of f0 minus f0 beta to the power d minus 1, and now I have to look up the expression because it gets complicated. Why should it be this series? Oh, because it's an expansion in beta, and these are the only possible terms that you can construct out of this G, I, J and AI, which are while invariant and diffeomorphism invariant. So the first term you can write down is cosmological constant. Then you have to go 2 derivative down, which is basically Ricci scalar and the f square. And then of course the more and more terms appears, but like conceptually this is the idea.
So I didn't quite see how you got the 1 plus omega I square.
Oh, it comes from the G hat because I didn't give you the complete expression, but the point is that the point is that if you evaluate the square root G hat after multiplying with this dilaton, it will have a omega dependence.
So the AI depends on omega in some way.
Yes, so AI depends on omega exactly, and the phi depend, and this square root G hat also depends on omega, and then this only comes after doing the integral.
This expression is same as the expression of Einstein gravity
Wait. Why do you get higher derivative Einstein gravity? There is nothing dynamical here. So it's the background is a complete background. So this expansion is just the expansion in beta.
So the R and expertors I can talk about
This R hat, so you basically put this on some manifold md minus 1, and this comes with this metric. So, and it's a fixed metric, no fluctuation, and you just evaluate this R hat f square from this metric. So there is there is no dynamical thing.
What I'm confused about is I can see that you will get like a beta coming from the fact that there is a tau. But where did the omega go into this? This calculation. So how do you get omega?
So the AI depends on omega.
So
Is that clear?
So it is chosen. Oh, I see. So the AI is.
So this factor is chosen in a way so that this thing doesn't have any twist. So this thing has so tau goes to tau goes to tau plus beta, and the other direction, and they cancel. So it's like a covariant derivative kind of an object. So that's how the omega dependence comes about. And then the phi also has a omega dependence. So you just have to write it down explicitly. Okay, good. And so you have this thing, and let me write down the full expression. So you have this f0 piece, and in fact I can factor this out. This factor is always there outside. Then I have this. Then there is a beta to the power d minus 3, which is d minus 2 times d minus 1 c1, the plus sign, and then you have 2c1 plus 8 over d c2, and then there is omega dependence and things like that. So this will be the expression for when you evaluate the partition function on S1 times SD minus 1. Once you write this down and do the brute force algebra, it comes out that way, but I can give you a physical interpretation of why there is a pole at omega equals I. And the idea is that in some sense is computing something with rotation, and omega equals I corresponds to the fact that the great circle of SD minus 1 rotating with the speed of light. So you cannot move faster than light, and that's why you are supposed to see a pole at omega equals I. And omega equals I just because I am writing down in the e power twice pi I omega form, like is the Euclidean versus Lorentzian thing. So you would expect that there is a pole at omega equals I from this. So there is a physical expectation. And as far as the calculation goes, that it just comes out of this analysis. Like you just have to write down the metric and just brute force calculate it.
So the while and diff invariance is what is forcing the d minus 2 power not.
Yes. Like, yeah, you cannot down by one derivative because you have to take exactly. Okay, so now we want to, so now there are 2 points. One point I already mentioned before that. So now we want to compute, okay, which one I should delete this probably. How much time do I have actually? Okay, I have some time. No, I want. Yeah, no. I'll finish before time. No worries. Okay. Oopsie. Okay. So now we have this expression, and now we want to look at our old like the quantity we wanted to study first, which is trace.
Invariance of the CFT. I mean, there is this higher dimensional central charges.
No, as such, as far as we know right now, there is no relation. Yeah. So this doesn't. Yeah. So that would be very interesting if there are some relations, but yeah.
But in 2D there.
Yes, in 2D there is. Yes, in 2D you have some more information that C is the central charge.
But in higher dimensions also there are notions of central charge.
Yes, it comes with the. Yeah, they doesn't appear here. As such, like as far as we know that they doesn't appear, but maybe there is some no relation with that.
For instance, for Yang-Mills theory, n equal for super Yang-Mills, probably maybe you can at some limit you can compute it.
Yeah,
maybe, but I guess you assume that it's also strongly coupled.
Here, well, we assume there is no zero mode.
There is no gap.
Yeah, there is no gap. Otherwise, there will be log beta corrections and so on, and you have to keep track of that.
But so like for instance, if you just take a bunch of free theories, you reproduce this?
Yes, of course, yes.
But there you can compare it against the central charge of that theory that doesn't match with any F0 or something.
No, I mean it doesn't match. I mean they are all numbers. You can always multiply with something, but
if you have a larger theory, maybe it will have some n dependence.
Yes. So the point is that you can do the following thing. You can compute it in some ADS car black hole, and it will have this same expression, and that will completely determine all these coefficients. So that's another important point, that normally in ADS3 when you match with the BTZ black hole entropy, you just have to match a single quantity, which is central charge, and you're done. But in hierarchy, basically it determines you this whole set of coefficients. It tells you the holographic CFT has to satisfy this, at least in the large n limit. All this F0, C1, C2, everything is determined once you compute the entropy of the black hole.
Yes. So so I'm just saying that at the leading order, I feel like that first piece, it's not fixed in terms of n square or something like that. So
Oh, this should go like n square. Yeah. It should be proportional to n square, but then there is no monotonicity property or is. Yes. Yeah, I would, yes, exactly. I would imagine that would happen, yes. Yeah, so whatever formula I am giving you right now, we basically checked against holography and like zillions of free field theories with all sorts of rotations and symmetries and so on. Okay, so these are the effective field theories. Now I want to compute this other quantity, which is trace e power minus beta h minus 1 to the power j, or in general e power twice pi I p over qj, and we want to write down some similar kind of expression. But at first glance you might think that I just have to substitute beta omega with this half, but as I was explaining that because I am taking beta going to 0 limit, omega goes to infinity, so I cannot use this expression to predict this. And in fact it is very much clear in 2D, because in 2D the relation is this. So if you just substitute beta omega with half, you will get a wrong result. And okay, so we have to be a bit more clever. And so we go back to the basic, and we want to understand how we can derive the 2D result in a different way. So now I will again go back to 2D and derive this result using some path integral formalism, and then you will see that easily can be generalized to the higher dimension. So what is this quantity? So this quantity is the following, where basically you take a torus. So this is my beta, and you divide the torus into two pieces. This is L over 2, L over 2. Now because of this minus 1 to the power j insertion, as you go advance by beta in the time direction, your cycle rotates by pi, which basically means that this piece is identified with this piece, and this piece is identified with this piece. Is that clear? Now what I will do, now I will realize that this thing is identified with this thing. So I will simply use the fact that in path integral I can do things cut and glue. So I can cut this piece from here and I will stack it on top of it. So basically I will take this piece, and this is my dotted line, this is my other line, and this is this. And this thing is identified with this thing now. And now this length is twice beta, and this base manifold is now L over 2. So now I can think of applying the EFT on this stacked manifold, where the effective length is twice beta and effective volume is L over 2. And recall that there is a volume factor which would get a factor of half, and each of the beta gets scaled by twice. And in 2D I know it goes like 1 over beta, so in 2D the Cardy formula goes like this, right? 4 pi square over beta C over 12. So another way of writing this is twice pi, and the volume of the circle is twice pi. But now beta goes to twice beta, so I have 2 factor here. L goes to L over half, so there is another factor of half, and that exactly give you 1/4, the one I had using the modular transformation. And now you can imagine what will happen if you have P over Q. You basically have to take into Q pieces, and they rotate among themselves, and you just cut them and stack them on top of each other. And once you do the stacking, the rule would be same. The beta goes to Q beta, and your volume gets 1 over Q times volume. So that explains this factor 1 over Q here, and this beta goes to Q beta gets explained here.
So it's, I think it feels to me that it is kind of crucial for this cutting edge stacking, that this horizontal direction has to be periodic. Is it periodic or compact maybe?
Yes, compactness is important.
Yeah.
Yes, so I will always be applying to, so this.
Otherwise you'll have to specify boundary conditions.
Yes.
And it will,
Yes, so yes, exactly. So the point is that there will, well, that's there, but I guess also there's another point that because you are looking at some long wavelength limit or beta going to 0 limit, so here also like there is some identification.
Beta going to 0 limit, when it is compact, is the same thing as this thing going to.
Yes, exactly. Yes, exactly. So, and that's why this identification, so there is some identification which I have not mentioned, right? This one and this one. So these are the like boundary conditions. And the idea is in the beta going to 0 limit is same as L going to infinity, and in this limit, this boundary condition doesn't matter. Okay, good. And you can also see there is no dependence on P anywhere in this expression. And
so in a sense, one could see this as the bare minimum necessary condition that is actually required for 2D CFT to be modular. I mean, to keep the Cardy formula. It's modular invariance is sort of like a overkill.
Yes, exactly. Yes, exactly. So the modular invariance has lots of extra information. So the bare minimum you need is this thing. That's it. And this procedure has nothing to do with the fact that this is a S1 on this direction. It can be SD minus 1, and you can play the same game. And if you play the same game, the rule would be again like you have, so a concrete prediction would be that the leading term, because it's beta to the power d minus 1, you'll get a q to the power d minus 1 from here, and the volume gets a 1 over q. So the leading term will always have 1 over q to the power d factor.
So in the beta, so let me give this a nice picture. So, so the basic point in some sense, the beta going to zero limit sort of, to kind of gets rid of the need. So makes the effective this thing non-compact.
Yeah.
And because of which you don't need any boundary conditions.
Yes.
So that
Yes. Exactly. Yeah. Yeah. In fact, so one more comment since we are on this point. This trick can also be applied for massive quantum field theory as long as you phrase it in the large L limit. So you cannot phrase it in the beta going to zero limit. Then the thermodynamic limit would be large length limit, and you can play the same game. And this relation will also hold for a massive quantum field theory, and you can check it for a massive QFT like we did massive scalar field theory. This holds. Large L. So in CFT, small beta, large L is same because everything is a function of beta over L. But in a QFT, you have other scale, for example mass, then you need to differentiate, and then I am saying the proper limit is the large length limit rather than beta going to 0. Oh, the idea is same. So now in 2D you had this S1 in this direction, but now you have SD minus 1. So you just have to imagine two hemispheres, and as you go in the beta direction, the hemisphere gets rotated, and you then stack them towards each other.
Why doesn't this argument doesn't depend on one plus 2D? That's the statement.
Yeah, and in fact it doesn't need to be SD minus 1 also. It can be any MD minus 1 as long as it has this isometry. Now I can be bit more specific, like what I am doing here, like in terms of math. So what I am doing here, this manifold can be described as doing a partition function on this manifold. S1 twice beta, Q beta. So it is like going to the qth cover and then quotienting by this ZQ. And this ZQ acts like this. So there is a unit vector on this sphere, and there is time, tau. So it basically.
I didn't follow. What were you doing here? Sorry.
So I am just mathematically expressing what the. So earlier I said that it's basically Z gapped MD minus 1 or Z of S1 times. Now I am phrasing it in terms of this language. So it's like if you go to the cover, this is S1 Q beta times SD minus 1. So this is this piece, like this whole piece, and then you have to quotient by ZQ, where the action of ZQ is this double action where you rotate the unit vector by some rotation matrix, which is a Q order, and you have to transfer tau to tau plus beta. So now the idea is that this is a non-trivial manifold, non-trivial bundle, because it acts on both n hat and tau. But in the beta going to zero limit, you can treat it as if this is S1 Q beta times SD minus 1 slash ZQ. So that's like your base manifold, and this is where you're doing the KK reduction. And for this you have a factor of Q beta, and for this you have 1 over Q. So that's a more, and the advantage of writing it this way to point out two crucial things. One thing is that this manifold and this manifold is not same, because globally they are differently identified. So there are some global distinction between these two manifolds, which again has to do with the fact that there are actual identification. So usually they do not matter, but then if you look at nonperturbative corrections, they might matter. And if the CFT has some gravitational anomaly, then also they can matter. And in fact, a concrete example is, again, we can go back to 2D CFT, and you can consider a CFT where C left is not same as C right, but C left minus C right is 0 mod 24, so you can still use the modular transformation. And then you will see that then the result is like if I do trace e power minus beta h, e power twice pi I p over qj, then the result is exponential 1 over q square, 4 pi square over beta, c over 12. But that's not all of it. You will also have a term twice pi I, cl minus cr over 24, p inverse q. So this comes from the modular transformation. And this is, I am not going into details, but the fact is that you can write it this way, but then you have to remember that there is some identification, which basically means there is the A field I wrote down initially, which keeps track of the small rotation. Now this A field has a large holonomy, and this holonomy is basically captured this identification. And this large holonomy thing can couple with the particles, like can couple with the state which has a non-zero spin. And because in 2D CFT, if I have Cl minus Cr non-zero, then the ground state has a non-zero spin, and this non-zero spin can see the holonomy of the A field along this direction.
Do you have any examples of that in the higher dimension?
In higher dimension, like we can see some such terms, like if I do like Dirac fermions in like electromagnetic, but then we do not completely understand it systematically. Like in 2D, we know that this is, so in the effective action, this will be some Chern-Simons term in 0 plus 1D, because like you are going one dimension down, and Cl minus.
So you can determine this directly from modular invariance. Right?
Yeah, you can either, so the point is, yeah, either you can determine it from modular invariance, or you say that there is a Chern-Simons term with level k, this is an integer, and it couples with the holonomy, and this holonomy is exactly P inverse Q, which basically sees the global structure. So in higher dimension, in principle, you can have some such terms, but we do not have a systematic understanding. But yes, Cl and Cr are the. What, sorry, this C is Cl plus Cr. Yeah. So.
Suppose you take the CFT of a flat space
Mm-hmm.
and do an expansion of this kind, at least the first term,
Mm-hmm.
if not will match with a flat space CFT. Suppose you take the CFT and flat space, meaning R theta.
Oh,
R whatever, D minus 1.
Yeah, I would think so. It will be just the free energy of the thermal free.
The free energy.
Yeah, exactly. Yes. Yes.
And then the higher order, like the omega terms should relate to the chemical potentials.
Yes, exactly. Yes. The omega term would be, so this term I think is related to the fluctuation of the charges, like some variance and so on. Yeah. So that's why I was saying you in the morning, in the Wayne model, I think you do not have this term, which basically says in the large n limit probably this goes like 1 over n or something, but you do have this term which goes like beta omega square, and so, and in your example you basically know all this code.
If you do the same computation on S1 times S D minus 1, you should get similar expansion.
Yes, yeah. Right. Okay, and there is one more point I want to make. Oh, sorry. The is the expansion. Yeah. Yes, exactly. Yeah. But the point I wanted to make earlier, that this argument of stacking argument, it doesn't rely on the fact that it's CFT. So this relation holds irrespective of it's CFT or not. The only thing, when you expand both sides, you want to use that expansion, then you have to use some extra input. Yeah.
So this one, we just need to take L to be large.
Yeah.
For a non-CFT.
Yeah, and you can fix beta and take a capital L to be large. Yeah, that would be the expression. Yes.
But this expansion is not guaranteed to be like this structure or this structure.
You mean whether the expansion converge or not? Sorry.
Can I write down similar expansion? I mean, in principle you can write down a beta expansion,
Mm-hmm.
but the coefficients are like only R and H squared like that.
Oh, in arbitrary QFT? No, in arbitrary QFT there will be other parameters. So this expansion won't be like this. But all I am saying, to derive this relation, you do not need that expansion. You only need this thing. But yes, this expansion is only valid for CFTs, not for massive QFTs. Because definitely you have other terms which can go in and make up for the dimension. Okay, so now I want to make a couple of more points. So this, up till this point, so basically I have this piece here, and I also told you that there can be one subtlety, which is this topological piece. So I write it down as A is topological. Maybe I should put a minus everywhere. So this topological piece will basically see that this global structure of the manifold, whether there is a P or not, no P. So that thing is there. So that's one subtlety. And there is one more subtlety which I have not yet mentioned, which doesn't happen in 2D, that when you do this rotation, for example, consider S2 times S1, there is a north pole and the south pole which are the fixed points of the rotation. Like whatever you do, the north pole and the south pole are the fixed points. Which basically means that this, you have to write down some other EFT coefficients. So you have to write down some extra EFT data which has support on this north pole and south pole. So these are like defects in the base manifold as you take the beta going to 0 limit. And so you will have some extra piece which I write it down as S defect. And this will only happen if there is a fixed point of this quotient. For example, it will happen in S2 times S1. In fact, it will happen in any S even minus S1. And if you have a odd dimensional S times S1, then it might or might not happen depending on how you are turning on various Cartan direction. So the point is, when you do this rotation, as soon as you have some fixed point or fixed locus, you have to, there is some extra contribution coming from writing down some terms on this S defect, writing down some terms on this fixed locus, and there will be some extra contribution. But this contribution will always be suppressed. So that's the important point, because this fixed locus will always be higher codimension. So their effect is always subleading compared to this piece here. But in principle, they can compete with all these other subleading pieces. And now let me write down the expression for the S defect and tell you. So now you may ask that what is the check of this fact that there is a S defect piece. And the check is the following, that you basically yes, yeah. So you start with this free scalar field theory in 3 dimension, S2 times S1, and you try to compute this quantity, or e power twice pi, and you can write it down in terms, because in free field theory everything is a word counting problem. Basically you construct all the operators, so you can compute this quantity explicitly using plathistic exponential. So you can do the beta going to 0 expansion of this quantity in the free field theory. And then you can indeed see that there is this structure that, like, you can forget about the topological term for now, but there is this, some pieces satisfy this rule, and once you subtract out these pieces, the rest of the pieces is like S defect. So there are some extra contribution. Now there are some nice checks. For example, if you do S2 times S1, the fixed points are the north pole and the south pole. And you remember I told you that here this pole is there because there is a rotation and something cannot move faster than light. But then on the north pole and the south pole, these are fixed points, these are points, there is nothing to rotate. So you would expect there is no pole. If I write down this S defect as a function of omega, so here also, okay, I should mention here, I can turn it on this beta omega j, here also this will be I omega j, and then this will be a function of omega. And now the point is, I will expect for S2 times S1 there is no pole in the omega. And indeed it turns out that once you write down the effective action, you will see that all the terms you can write down, there is no pole in omega. You can check in free field theory that there is also no pole in omega. And for completeness, let me write down the expression, let me write down the terms that can appear, and I will be done in 3 minutes. So the terms that can, at least so you can do this game for any dimension, but let me do it for S2 times S1, which is simple. So this basically tells you that defects that comes from the rotation P over Q. So the first piece will be a constant piece, which is this. The cosmological constant evaluated at that point. The second piece will be suppressed in Q beta. Then there will be some Wilson coefficients, P over Q, and then there will be Hodge dual of F evaluated at that point, and then you will have Q beta square, some A2 P over Q, Ricci scalar evaluated at that point, and then you have some A3 Q. So this is like F square, and so on. So this will be the general structure.
So you haven't told us how to determine these terms, right?
No, I haven't told you. So the idea is that you want to write down terms which are invariant under this action. So basically you look at all the diffeomorphism and the while invariant terms on this manifold and make sure they are ZQ invariant. And then you can systematize them. And that's why you basically only can write down constant P's and Hodge-do all this R and everything like that. And in higher dimension, you can like have multiple defects which can cross each other and so on. And then basically you have to systematize the whole thing. Like if you look at locus of this rotation, then you have to make sure that it is invariant under that ZQ and the other terms. So yeah, it's basically accounting, like systematically writing down all possible terms. And so you can again evaluate this for S2 times S1. There will be a north pole contribution and there will be a south pole contribution. And all these coefficients, another important point, this P over Q has a periodicity 1. So that basically means that half and minus half will give you the same contribution. So that gives you some consistency conditions on this EFT data. And again, you can check in the free field theory, those consistency data are matched. And you can also check in the holography. So in the holography, the idea is that if you forget about this quotient, this gives you some black hole solution. And you extend this black hole solution and you extend this thing in the bulk. And that gives you some quotient of the black hole, and that explicitly reproduces this thing. As long as you don't have any fixed points, this is a smooth solution. And if you have a fixed point, there will be some defect. And then there should be some extra data which resolves the defect, which we do not know as of yet. But the thing that resolves this singularity will also determine all these coefficients for the holographic CFTs. And what, did I miss anything? Okay, I should one more point. So all I have told you about bosons. For fermions, you have to just keep track of the spin structure, because when you stack two of them, the antiperiodic can become periodic. So you have to keep track of the -1 to the power. So if you forget about everything from the talk, I want you to remember 2 points. That if I tell you trace e power minus beta h and trace e power minus beta h minus 1 to the power f, if I give you these two expansion, all the Wilson coefficients, up to these defect terms and topological terms, you can determine all the things, all the grand canonical things which are determined by P over Q. So that's the main punchline. So in higher dimension, you do not have modular invariance, but for a large extent, everything is determined by the leading expansion, like by the expansion of these two quantities. Okay, thank you. You mean for the massive? Well, it will be, yes. I think so. This you can say the same thing. Like here, you have a Q beta. If you take beta going to zero limit, this goes away. So in the same sense, SD minus 1. If you take a large limit, there is a fixed point. It will be suppressed in probably 1 over L, and in the L going to in the radius going to infinity limit. It,
when S1 times SD minus 1, then this kind of term might appear because of the rotation.
yes.
So if it is, you are taking the large radius limit of that SD minus 1, then it shouldn't be there.
No, it should be there. It should just be suppressed in 1 over L. So here also it is suppressed in Q over beta, Q beta. So in the beta going to zero limit, it goes away. So in the same way, if you take the strict limit, it will drop out. But there will be some 1 over L. So in fact, it will be beta over radius kind of suppression.
So there was, I remember that about a decade ago, there were some papers by Edgar Shagulian where he was doing something of this kind of thing. I found them to be somewhat, I don't know, I never studied them properly, so I don't know what to do. But was it as, it seems like kind of systematic in some way.
Yeah, so this is what, no, so I think, so what Edgar did, he first did, well, it's still recorded. Okay, so it's S1 times S1 times S1, so series of S1s, and then you can swap them, any S1s, so that works perfectly, but then you do not have any relation with the operator spectrum, because there is no state operator correspondence. And Edgar also looked at length space. Some quotient of S3, and then he has two kind of quotienting on this side and on this side, and then you can exchange the quotienting and relate the low temperature in the highly length space to the high temperature of the low length space. Yeah, so this is much more, this is way more symmetric, systematic way of doing things, and in some sense, this expansion is still, one can argue that this expansion was there in Siraj's paper, in the hydrodynamic paper. But the completely new thing is this trick and this idea of stacking it and expressing it in terms of this manifold. That's completely new, and and I think it's not. In fact, as you see, that this trick is very general. As long as you have a compact manifold with some isometry, you can play the game.